hi AP Stats. This is our first part of notes for Chapter 5, Section 3 about conditional probability. So we've already talked a little bit about conditional probability earlier in the year when we did two-way tables. So here's the official notes that kind of go with them, except we're going to add in some new notation this time. So conditional probability is the probability that one event happens given that another event is already known to have happened. So it's the probability of something happening when you already know that something else has happened before it. So the way that they write that is they use the P for probability, and then they say event B, we want to know the probability of event B, and then this vertical line is the part that says given that event A has already happened. So you'd read as probability of event B given that event A has already happened. All right, so here we have one about whether people graduated from high school and whether they're homeowners or not. And the first example says, if we know that a person owns a home, what is the probability? So we already know this is the given part, right? They already told us this is the given part. Okay, what is the probability that the person is a high school graduate? So we're looking for what is the probability that they're a high school graduate knowing that they own a home. Okay, and I would actually prefer that you write it this way where you actually explain what it is than just saying B and A, because then you'd have to identify what B and A is off to the side and identify your variables. So this way it's a little bit easier. So probability of high school grad given that they own a home. So that means that anything under here is the denominator, right? So denominator is going to be how many own a home. So homeowners, if I go over here, is going to be this number right here, 340. And then the top part is going to be, the numerator is going to be the high school grad that is part of that list, right? So that means I'm looking only in this row. That's the only numbers I can use to add up to 340, and which numbers that make the 340 are the ones that are high school grads. So that would be the 221. Okay, all right, next one, let's try another one. And I'm going to erase all the stuff we just did on the table here. Okay, so on the next one we have if we know, so there's the given part, that person is a high school graduate. What is the probability that they own a home? So now we're doing what is the probability that they own a home given that they're a high school graduate. All right, so once again, this part is your denominator, whatever is in the given that part. So high school grads, that would be, we're looking in this column. So we would be looking at 310 for our denominator. And then of that 310, how many of them own a home? Well, that would be the 221 as well. All right. And they said, are these two probabilities the same? No, they're not. They have different denominators, but they have the same numerator, right? So it says why or why not? Well, because they're using different groups, right? The top number is the one that has both in common, but the first one was how many are high school graduates and own a home from the own a home group. And the second one is how many own a home and are high school graduates from the high school graduate group, okay? And you think order matters when calculating conditional probabilities. So yeah, they absolutely do. Right? Because if I put the wrong given that on the wrong side, then I have the wrong denominator to work with. Okay? So are the two probabilities the same? No. Why or not? Why not? Denominators are different. Okay. All right. So the next part is they're going to show us some formulas on how to do conditional probability. So again, this is just basically the idea that we just used. So I'd much rather you understand the idea behind it than you memorize a silly formula. And on the actual AP, a lot of these formulas are given for you already. In distance learning, we're using these formulas already. So the main idea here is that if we're looking at the formula, remember this is the given that. So notice that this becomes the denominator. And then this has to be the numerator, but it has to be from the subgroup of B. So that's why it says it has to be A and B, okay? And then if I switch them around, well then A is the denominator and the top has to be B, that's part of the A group, okay? So here's another example, kind of doing the same thing, except this time they gave us probabilities. Do we care? No, it still works exactly the same way. So what is the probability that a randomly selected household with a landline also has a cell phone? So are they asking what's the probability of a person having a landline, Are they asking what's the probability of them having a cell phone? If you just had to shorten the problem, you would say, what's the probability of them having a cell phone? So this is probability of cell phone given that they have a landline. Okay, so if it doesn't automatically say given that, think to yourself, what's the part that I could take out and just say, what's the probability I'm really looking for? What is the probability that a randomly selected household has a cell phone? That's the main part. And then they're saying they also have a landline. So landline becomes the part at the bottom. Okay, all right, so here we go finding out our probabilities. So landline is on the bottom. So we're looking in this column right here. So that's going to be a 0.6. And then of that, how many are cell phones of the landline? So see, these people are going to be cell phone and landline together. So that is 0.51, and then you would just reduce that, okay? This was the part we also talked about don't just do this in your calculator and write out the final thing. They want to see the numbers where they came from in the actual table. Okay, so put the numbers down from the actual table first, then you can simplify if you want to. All right, our next one, it says, what is the probability? So let me erase all of this stuff. Okay, so this time we're going to do what is the probability that a randomly selected household with a cell phone also has a landline. So the main part here is what's the probability that they have a landline given that they have cell phones. Okay, so now this time cell phones is on the bottom. We're looking at this part. We're looking at 0.89 and the landline and cell phone is still 0.51. Okay. All right, so we've kind of practiced that, and it says it doesn't matter whether it's probability numbers or count numbers. When we're doing probability numbers, if we do counts, they turn into percents, and if they're percents, they're still going to stay percents. All right. Next one, again, it gives us a rule first, but I'd much rather you understand what's really happening here. And this one says the probability that events A and B both occur can be found using a general multiplication rule that says if you want A and B to occur, you have to multiply the probability that A happens times the probability that B happens, given that A has already happened. That kind of makes sense, right? If you want to know, both of them to happen, you kind of have to know that the first one already happened. Okay. All right. So let's take a look at what that would look like. All right. So the first part says example 6, 93% of teenagers use the internet, and that 55 of the online tests have posted a profile of online teens. Have posted a profile on a social networking site. What percent of teens are online and have posted a profile? So this one is not a given that because I can't see that they're just asking one thing. They're asking the two things, online and posted a profile. So we're doing what's the probability that they are online and, you can either write the word or the symbol, posted a profile. Okay, let's go see what they gave us. So they said 93% are online, right? So that's the first one. And then this one says it's 55 of the online teens. So 55 definitely comes after they're already online. So another way to say that is we could say the probability that they are, let's see, how would I put that? That they have a profile, given that they're online. Okay, so filling that in, we would end up doing 0.93 times 0.55 because they want the ones that are both in both of those groups. So we want the overlap of the ones that are on the internet and the ones of the online teens that posted on social media. All right, one of the other ways to organize stuff. So in the last section, we talked about using tables or Venn diagrams. One of the other ways that we can organize some of our work is using a tree diagram. Now, a tree diagram is fantastic when we are talking about stuff happening in sequence, and that's really the key idea for a tree diagram. So we want to do a tree diagram where we can purposely see this happened first and then that led to the second thing. So since I have more room going sideways, I'm going to make my tree diagram going sideways. So the first thing that they segmented out for us in the prior example was that 93% of teenagers use the internet. And that was kind of just a probability on its own. It was only attached to internet. So I'm going to say that this is online, right, that they have the internet. And there was 93%, I believe, that were online. Let's double check. Yes. So 93%. So I could subtract that from 100% and know that this has to be 7% would be not online. Okay, and then if they were online, there was also the possibility that if they were online that they posted a profile. And we said that the posted a profile percent was 55%. That means that the other one, if I subtract it from 100%, has to be the opposite, which is not posted a profile. So if I'm going to work my way through a tree diagram to get to online and posted a profile, then I'm going to need to follow along that tree and multiply everything that comes along in its way. So I want to start out with this one to get to online, and then this one to get to posted a profile. So that's how we're going to work that. So then the probability becomes 0.93 times 0.55, just another way to organize. And this is by far my favorite way versus just using the formula that we did in the previous example. All right, so let's see if we can do another tree diagram down here and see if we can practice this one more time. So late for school. Shane hits the snooze bar on his alarm clock on 60% of the school days. If he doesn't hit the snooze bar, there is a 90% chance that he makes it to class on time. However, if he hits the snooze bar, there's only a 70% probability that he makes it to class on time. So on a randomly chosen day, what is the probability that Shane is late for class? All right, so let's take a look at what we are looking for here. So here, the first thing is if he's only late or not late, depending on whether he hit the snooze bar. So in order, it's snooze bar before being late. So I'm going to try to set it up that way too. Now, sometimes I'll set it up in the wrong order. I'll just misread the question, or it wasn't clear to me which one happened first, and then you just erase and go back and start the tree over again. So I'm going to say that the first one is that he snoozed, and the other one is not snoozed. Okay, so he said 60% of the time he hits the snooze bar. That means 40% he doesn't. Okay, and then it says if he doesn't hit the snooze bar, so that's this part down here this time, there is a 90% probability that he makes it to class on time. That means that there's a 10% chance that he makes it to class late. Okay, so same two categories up here. We would have on time for the top part and late for the bottom part. Okay, they said, however, if he does hit the snooze bar, that's the 60% one, there is only a 50 or 70% probability that he makes it to class on time. That means there's a 30% if I subtract it from 100 that he is late. All right, so next we want to see what is it that we're actually trying to follow. So they said on a randomly chosen day, what's the probability that Shane is late for class? That's all they want. Now here's the thing, is we were given information about the snoozing before him being late. So we just can't say he was late 30% of the time or 30 plus 10, right? I have to follow the sequence of events. So I'm going to have to travel this way through the 60 to get to snoozed, and then late, that's this one. But there's another way he could be late too, and that's going this way. So I'm going to have to add two probabilities together. So this is going to be 0.60 times 0.30, and then we're going to add that to the other way he could be late, which is 0.4 and 0.10. Okay, so the one way was being late and snoozing, the other one was being late and not snoozing. So we can work it out that way. All right, one of the most challenging things to do is to work your tree going backwards. So let's show you what that looks like. So we're going to use the same example with Shane being late for school. And it says, suppose that Shane is late for school. So we already know that he's late. What is the probability that he hit the snooze bar that morning? So this is like a given that he's late, right? So the probability is something given that he's late. So sorry, I don't have to write given that, right? Given that he is late. So snooze. So I'm going to use that same tree diagram, but we're going to go back to that conditional probability again and make this our denominator. So how many different ways was he late? Well, that was the answer in our previous one, right? So that was the 0.6 times 0.3 plus 0.4 times 0.1. Okay, so there's our late. Those are all the ways we could be late, either traveling the first pathway or the bottom pathway. So we want the one where he snoozed. Well, that's the top pathway, and I want to go all the way to he was snoozed and was late. Don't just stop at snoozed. We have to go to snoozed and was late because our denominator is late. So it's going to be one of these two down here, and you're going to use both of them and take it all the way to the same position in the tree that your denominator goes to. So I want snooze and late, that is the 0.6 and the 0.3. So you would write all of this up before you grabbed a calculator and simplified it down to an answer. Awesome? All right. One more, I think, maybe a couple more. Okay, so one more. Many employers require prospective employees to take a drug test. A positive result on this test indicates that the prospective employees used illegal drugs. However, not all people who test positive actually use drugs. Suppose that 4% of the prospective employees use drugs. The false positive rate, we'll have to talk about what that is 5%, and the false negative rate is 10%. So a randomly selected prospective employee tests positive for the drugs. What is the probability that he actually took the drugs? All right, so we're looking for what is the probability. Oh, before we do that, let's think about if we're going to do a tree diagram, because this definitely has something happening first and second, right? He has a drug test, right? And then there's he did or he didn't take drugs, right? So pretty much you'd be taking the drugs first and then testing. So when we draw our tree diagram for this, that's what we're going to be looking at. So the first one is going to be took the drugs, and the other one is no drugs. So do we know those percentages? So I'm reading back through and it says, suppose 4% of employees use drugs. Okay, so that's this one right here, so 4%. Okay, that means that the other one is 96%. Okay, so once they took a drug, they could either have tested positive, or they could have tested negative for the presence of the drugs. Okay, so if they took drugs and they tested positive, that's what you would expect to have happen. That means the test would work right. If they took the drugs and they got a negative test, that means something happened wrong. So we would call that a false negative because it's something that happened wrong. We wouldn't expect that to happen. Okay, so let's see if we can figure out those. So we are looking for some of the other numbers. Let's see, a false positive, no, we have a false negative. So a false negative is the 10%. So that means this is the 90. Okay, so I'm going to double check here and write and say this is a false negative. We got a negative result on the test when we shouldn't have. All right, that means on here I'm going to have the same thing happen. The person was not using drugs. They could test positive or they could test negative. Okay, what's supposed to happen? Well, if they didn't take drugs, their test should come back negative. That's the correct pathway that it should go. If they didn't take drugs and they test positive, that's a false positive. We got a positive result when it really shouldn't have happened. Okay, so going and putting all of those numbers in. So we've already done the 10. So we still have a 5% for a false positive. So that's going to go right here. And that means 95 go over here. All right, so now we can start looking at the question. It says, what is the probability that he actually took drugs, knowing that he came from, that he tests positive, what is the probability? So how would I write this? This is the probability that he took drugs, given that he tested positive. What is the probability, right? So test positive. Okay, so that means I'm going to have to first work on that denominator, which is what are all the different ways that I can test positive. So I have first route, test positive. I could have used drugs and then tested positive, or I could have not used drugs and then still tested positive anyway. So those are going to be my denominator of my probability. So following that pathway, we're going to get 0.04 times 90 plus 0.96 times 5%. And then the top has to be one of those. So which is the one we want? We want the pathway where he did take the drugs. So that would be the 0.04 times 0.90. So you'd write that out and then simplify. Cool. It says, what happens if we change the test so that there are less people that test falsely positive? And what happens to the false negative rate? So let's go and take a look at this. So which part are they asking me to change? They say, what happens if we change the test so that there are less people that test falsely positive. So we would want this number right here to go down, right? So if we do that and that number goes down, then this number has to go up, right? So I'm going to end up with more false negatives. So they kind of react with each other, right? So if the probability of the test goes, the testing positive goes up, then 90% of the drug users caught would also go down, right? Because that's testing positive. This was testing positive. So the positive rate would just go down. There'd be less positive rates. So if there's less positive rates, then there'd be more false negatives. So it's kind of a trade-off with those two different errors. You can either reduce the false positive, then you're going to get more false negatives. Okay, and the same deal here is if I reduce this, then this has to go up because it still has to add up to 100%. So you also often have to think about which one is the worst of those and then say which one is the worst. And again, it's going to depend on whether you are the employee or whether you are the employer, right? So if I am the employer, I want to make sure that there's nobody using drugs at my company at all, right? So I'm willing to fire a few people that get false positives in order to keep the false negatives from getting through, right? So I would increase the amount of false positives. I might lose a few good people, but I won't have anybody using drugs in my company. But if you're the employee, you probably want it to go the other way, right? You don't want to get fired if you didn't take drugs. So you would want to reduce those false positive ones, right? So that you're not accidentally accused of something that was just part of the test error. Okay, so we could see that too. So if we lower the positivity of the test, of the no drug test, then we also lower the positivity of the took drugs test, right? It's still the same test. And if that happens, if we lower the positivity of the took a drug test, then we will be raising the negatives. Okay, all right, so those interact with each other. So if you reduce your false positives, you will be increasing your false negatives. Okay, and those work opposite each other. Awesome. All right, that is it for today. We'll see you next time.